Hello and welcome to another introductory statistics instructional video. Today we'll be talking about how to set up a simple linear regression in StatCrunch and what each of the things that it tells us in the output mean. For this example, I'm once again going to be using 1000 randomly selected video games. So to get started, you want to go to Stat, Regression, Simple Linear, and it'll bring you to this interface here. Let's say if we want to see the number of units sold in millions in North America can be used to predict the score that professional game critics give the game. Your X variable is always going to be your predictor or your independent variable, while Y is always going to be your response or dependent variable. I want to see if North American sales can predict critic score. So my predictor variable is going to be NA sales, and my Y variable is going to be critic score. There are a few other things that we can tweak in this interface, but for now, let's just go ahead and run it. So you can resize this to get a better view. This is what the output gives us for simple linear regression. It restates what our dependent and independent variables were. And then it gives you the regression equation, also known as the equation for the line of best fit, or the least squares line. Normally when you're seeing an equation, you would see y equals your y-intercept plus your slope times x. In StatCrunch, they just input those variable names instead of x and y. It will tell you your sample size and your correlation coefficient. This correlation coefficient R measures how strong of a linear relationship there is between your independent and dependent variables. So we've got an R value of 0.32, so that's fairly weak overall. And you will never, in my class, have to calculate R by hand. It's a pain to calculate, and the software can just do it for us much more quickly. You'll also be given R squared, which tells us the percent of variability in our response variable explained by this regression equation. So with an R squared of 0.1, that tells us that this model is only explaining a little bit of that variability, and the rest of the points scattered about are just due to random variation. You can also think of this as a measure of how much more effective it is to use this regression equation, rather than just predicting the average critic score for all possible values of NA sales. This estimate of error standard deviation tells us on average how far the points fall from the regression line. So those are all descriptive measures. Now we get into the inferential side of it. For the parameter estimates, you'll have one row for your intercept and then one row for that slope variable. Once we get into multiple linear regression, you'll have one row for every variable in the model. This first column here gives us the parameter estimates, which we can see back up here in the equation. It gives us the standard error of those estimates, degrees of freedom, a t-test statistic, and then the p-value. So what's happening here is each of these rows is testing whether the parameter in question is 0 or if it differs from 0, if the variable has a meaningful effect on the response. We never concern ourselves with the row for intercept. That doesn't really do too much for us. In later statistics classes, you would learn about a different form of regression where we actually do care about this, but don't worry about it here. Instead, you want to focus on this row for your slope. So what this t-test statistic and p-value tells us is that we have reasonable evidence to believe that there is a linear relationship between NA sales and critic score. We rejected the null hypothesis that the slope parameter was 0. Now this ANOVA table down here is not really relevant for simple linear regression. It'll come into play once you get into multiple regression. An interesting thing to note though is that this f-stat here is just the t-stat associated with your slope squared, and the p-value will always be exactly the same for simple linear regression. This is because the t-distribution and the f-distribution are related, but you don't really have to worry about that now. Now we have this arrow down here. If we click on that, it'll show us the fitted line plot for our variables. Here we can definitely see that there is a weak relationship going on. Now let's see what some of the other adjustments we can make under options. There's this button here for perform, where you can change from a hypothesis test to a confidence interval. What that changes is now back in that table for parameter estimates, rather than giving us that hypothesis test, it'll give us a lower limit and upper limit for a confidence interval for these parameters. Like all parameters that we try to estimate when we're looking at population means and population proportions, for example, this point estimate here is just our single best guess for what that slope parameter is. The likelihood that we got that slope exactly correct for the population regression line, very unlikely. So it helps to get a range of possible values for that slope. Another option down here, prediction of y. You can select an x value. Let's say we want to predict the critic score for a game with 2 million North American sales. Now we go back to the output, and it'll give us a new table down here at the very bottom. It'll give us the x value that we entered, the predicted mean critic score. It'll also give us a standard error for that estimate, and it'll even give us these two different intervals. A 95% confidence interval is giving us an interval for the average result for all games with 2 million units sold in North America. Prediction interval has a slightly different interpretation. The prediction interval tells us that if we were to randomly select some game that isn't in our data set that has 2 million North American sales, we would predict that one single randomly selected game's critic score to fall in this range. Notice that the prediction interval is wider than the confidence interval. That's because there's a lot more variability for a single observation than for the average of a bunch of observations. A few more options that we have. You can save some graphs, which will be useful once you get into checking assumptions for regression. We'll have another video going over how to do that. This save box is very useful because let's say we want to analyze those residuals. We can select that here, and then when we hit compute, StatCrunch will give us a new column at the end of the data set with the residuals for each observation. That about wraps up the basics of simple linear regression and how to navigate the output. Once again, there will be another video posted by my colleague that will explain how to check those assumptions and how to use those graphs. Alrighty.